Picture this, a bright yellow element that smells, well, let's be honest, exactly like rotten eggs. It's brittle, it's really not all that beautiful to look at, and yet it is the quiet engine that quite literally feeds the entire world. Welcome to this explainer. Today, we're putting a true foundational material under the microscope. We are conducting a highly rigorous, corporate-style performance review for what is, essentially, a pile of foul-smelling rocks. We're evaluating an element that has been utilized since the absolute dawn of civilization to build modern chemistry as we know it today.
And that brings us to the big, central question of our evaluation. Are we looking at an underrated, S-tier backbone of global industry? Or is this just a low-prestige, smelly byproduct of our fossil fuel consumption? Throughout this explainer, we're going to tease out the incredible tension between sulfur's absolutely massive industrial scale and the incredibly messy, toxic reality of actually handling it.
So, here is the rubric for today's performance review. First, the yellow cornerstone. Second, igniting human history. Third, specs and modern utility. Fourth, the rotten truth. And finally, we'll deliver the final verdict.
All right, section 1, the yellow cornerstone. Let's look at the elemental profile. We're dealing with a highly reactive, brittle nonmetal, often found out in nature as these bright yellow crystals or locked deeply away within sulfide ores. But here's what is absolutely vital to understand about how we interact with this element today. In 2026, we don't really mine sulfur directly out of the Earth's crust anymore. Instead, we recover it in absolutely massive quantities while cleaning up our fossil fuels. Through a process called desulfurization, as we refine petroleum and natural gas to make them cleaner to burn, we are just left with literal mountains of this abundant elemental byproduct. Moving on to section 2, igniting human history. Let's check out the resume.
You know, the ancient Greeks actually called it theon, directly linking it to the gods, and it's pretty easy to see why when you trace its evolution over millennia. Starting around 2000 BCE, ancient civilizations were already using it for fumigation and medicine. Fast forward to 1000 BCE, ancient Chinese alchemists are mixing it into early gunpowder recipes. By medieval Europe, it became totally infamous as brimstone, heavily associated with explosive warfare. And then we see this massive game-changing technological pivot in the 1700s and 1800s, where sulfur becomes the critical ingredient for producing sulfuric acid via the lead chamber process.
So sulfur isn't just some historical footnote. It is the absolute foundation of heavy chemistry. It was the crucial underlying ingredient that first sparked early explosive warfare, and then it impressively pivoted to become the foundational chemical driving the massive agricultural revolutions of the 19th and 20th centuries. It blew things up, and then, brilliantly, it grew things.
Section 3. Specs and modern utility. Let's dive into its skills and capabilities.
Let's look at the specific engineering properties that make sulfur so surprisingly indispensable to our modern way of life. Looking at its profile, it forms incredibly strong chemical bonds across a vast range of elements. It's highly acidic when converted into sulfuric acid, and in its pure form, it actually serves as an excellent electrical insulator. But its true superpower? That has to be its incredibly low melting point of just 115 degrees Celsius. Because it melts so easily, it's just incredibly simple for industrial plants to handle, heat up, and chemically convert into thousands of other compounds. Its workability is simply unmatched.
And that easy workability translates to a staggering scale, 80 million tons. As of March 2026, global sulfur production exceeds 80 million tons annually. Let that sink in for a second. That is an almost incomprehensible amount of material quietly flowing through the background of global manufacturing every single year.
So, where on earth does that 80 million tons actually go? Well, over 90% of this massive output is converted directly into one thing: sulfuric acid. Because of this near-total conversion rate, sulfuric acid sits as the single most produced industrial chemical on Earth. Only a tiny 10% fraction goes toward other direct industrial uses.
Let's look at the core modern utilities that demand all this acid. Above all else, it's required to manufacture the phosphate and nitrogen fertilizers that literally feed the global population. It's also essential for rubber vulcanization. That's what cross-links rubber to give us durable vehicle tires. It's heavily relied upon in mining and ore processing, and, fascinatingly, looking at 2026's next-generation energy tech, we're seeing emerging demand for it in high-capacity lithium-sulfur batteries.
Which brings us to Section 4, the rotten truth. Every material has performance flaws, right?
An honest, zero-mercy review means we have to confront a pretty dark paradox. We have unmatched utility,
I mean, it literally feeds the world and powers the heavy chemical industry. But that is balanced directly against a severe environmental cost. When mishandled, we are dealing with the severe odor and extreme danger of toxic compounds like hydrogen sulfide and sulfur dioxide.
Let's detail these core problems. Its emissions contribute heavily to devastating acid rain. Ironically, while it creates fertilizer, the agricultural overuse of sulfur products actually acidifies and ruins farming soil over time. Furthermore, because it's a byproduct, its supply chain is completely tied to volatile fossil fuels. And finally, let's be real, it completely lacks premium material prestige. Engineers and the public generally view it as a low-value, incredibly smelly byproduct, which is exactly why greener, non-sulfur substitutes are actively in development today.
All right, Section 5, the final verdict. It is time for the tier ranking.
Let's crunch the numbers across our criteria. For historical impact, it earns a massive 9 out of 10 for enabling modern chemistry. Its mechanical properties earn a modest 7. It's simple, though definitely functional. For workability, a 9 out of 10 for absolute ease of conversion. But look at those next two, near-perfect 9.5s in both scalability and versatility, all thanks to its cheap abundance and wide-ranging uses. Finally, it scores a 9 out of 10 in lasting relevance, as it remains completely irreplaceable in core global processes.
When we average those metrics together, we arrive at a final score of approximately 8.8 out of 10. That is an incredibly formidable number for such an ancient material. But where does it place on the definitive tier list?
Here is our official declaration. Sulfur is definitively a high A-tier material. It's the elemental workhorse of human industry. The only things blocking this element from achieving a perfect S-tier ranking are the severe pollution issues tied to its compounds and, of course, its complete lack of prestige and glamour. It definitely doesn't shine, but man, it works tirelessly.
There's a quote that perfectly sums up its role. If salt preserved food and nitrate grew it, sulfur fertilized it at scale. That captures its indispensable, albeit completely unglamorous role in human survival and progress over the last century so perfectly.
Which leaves us with this final thought. Without sulfur, modern civilization would quite literally starve and stall out. So, are we giving this yellow, smelly cornerstone of industry the respect it actually deserves? The next time you look at modern agriculture or heavy manufacturing, remember the silent 80 million ton engine running in the background. Thank you for joining me for this explainer, and keep learning.